feel super familiar to you guys. And part of the reason, notice that this is section 3.5, and you're like, what the heck, we just finished chapter 1. In terms of unit 1 for the College Board, once we complete this lesson, we'll have completed unit 1. I like to pull this lesson in because it is familiar to you, and it's limits. And we've just wrapped it, like we're trying to wrap up limits. The reason that this section is in chapter 3 is chapter 3 is all about curve sketching from a calculus perspective. So like we'll be referencing limits at infinity, like as x approaches positive or negative infinity, in that unit, but we'll just have already covered it. Okay, so we won't have to do the lesson when we're in chapter 3. But again, this should feel super familiar because anytime we're thinking about limits as x approaches positive or negative infinity, we're thinking end behavior, right? And so like previously, we've thought about end behavior. Remember where I would give you questions like, as x approaches infinity, f of x approaches fill in the blank, right? Where the function would either be approaching positive infinity, negative infinity, or a number, right? A horizontal axis. There would be a horizontal asymptote. So that's very much what we're still thinking. But now we have this new notation that we can slap on, thinking about as x approaches positive or negative infinity. So it's a limit, right? We're thinking limits. We've used the same language, but now we're using just the new notation. So some of this should feel very familiar. Like we're going to start with the limit as x approaches infinity of this polynomial function. Okay? And this hopefully does sound familiar to you. When we're thinking about as x approaches infinity, like plug in larger and larger and larger values in for x. I previously told you you can almost think about the terms as x gets infinitely large or infinitely small as we get at like a tug of war with each other, where which term is going to dominate the tug of war as x gets infinitely larger, infinitely small?
3x to the power.
3x to the 5th, right? The term that has the largest exponent, the term that determines the degree of the polynomial, is going to be the term that ends up dominating all the other terms as x gets infinitely larger, infinitely small. We can treat 3x to the 5th as our, remember this, end behavior model. Right, the EBM for this particular function would be y equals to 3 times x to the 5th. And what the end behavior model is, which we used last year as well whenever we were talking end behavior of a function, is it's a simpler equation that you can analyze for end behavior, or you're maybe just familiar with end behavior, that the more complicated function has the same end behavior as. So it's a simpler equation that you can analyze and determine what's happening to the function as x gets infinitely larger, infinitely small, in order to determine the end behavior of the function that you're really concerned about. So like that 5th degree polynomial that has multiple terms has the same end behavior as y equals 3x to the 5th. So we can just think about, okay, as we're plugging, if we're thinking about x approaching infinity, so plugging in larger and larger values in for x and then raising to the 5th power, what's happening to those values? They're getting bigger and bigger. And then if you multiply those bigger and bigger values by 3, they're continuing to get larger and larger and larger, meaning that this function that has the same end behavior, similar end behavior, will be equal to, the limit will be equal to positive infinity. kind of the more pre-calc perspective would be like, hey, I'm looking to the degree of the polynomial and the fact that the leading coefficient is positive. So that indicates that for end behavior would be similar to a positive sloping line. Right? Remember the pre-calc books always put like a chart in and they're like, odd degree polynomial, positive leading coefficient, end behavior is similar to a positive sloping line. Which that works too, right? Because then you're thinking, okay, as x approaches infinity, this polynomial function will approach infinity just like a positive sloping line. Yeah?
Yes.
Okay, what about as x approaches negative infinity? Negative infinity. So both of those limits technically don't exist, but we've given the more specific answer that describes why they don't exist and also gives us a snapshot, kind of a blurry snapshot, but a snapshot of what the end behavior is like for these particular functions. We okay so far? I don't know why I'm standing so far away. Okay. E to the negative x. Now, you guys have studied y equals e to the x. Let's think about what that graph looks like. It's an exponential function. Graph would pass through 0, 1 and exhibit exponential growth. Right? This is a parent function that we studied. But listen to what I'm saying too. I realize even if you can figure it out, listen to what I'm saying. Okay.
You literally asked me what I got.
So y equals e to the x. This graph should be familiar to you. If we think about e to the negative x and what that graph looks like from a transformations perspective, what's that negative doing to the graph of e to the x? A horizontal reflection, right? A horizontal flip. And from also being familiar with the graphs of e to the x, and then when transformations are applied, we had previously talked about the end behavior of e to the x. That's just one of the characteristics that we previously talked about. You guys know that there is a horizontal asymptote, or hopefully you remember that there's a horizontal asymptote that describes the end behavior at y equals to 0. And that kind of goes along with that graph. So from a kind of just being familiar with e to the x and knowing e to the negative x, what that would look like from a transformations perspective, you could say that as x approaches infinity, e to the negative x would approach 0. Is that kind of how you thought about it?
Yeah.
The other way, the other approach, so you could bring in some of your new knowledge about limits and limit properties, is you could go, hey, how could I rewrite e to the negative x?
1 over e to the x.
Using exponent rules as 1 over e to the x. And then you maybe didn't necessarily write this step out, but if you were to think about using the limit property, for a quotient, thinking about the limit as x approaches infinity of 1 over the limit as x approaches infinity of e to the x. Well, you're this limit goes to 1. As x approaches infinity, what does e to the x go to? Infinity. If you have 1 over infinity, what's that equal to? That limit equal to? 0. So kind of tapping into what we just had previously talked about. right? Thinking about having that 1 over infinity and what that means. Now, e to the negative x, as x approaches negative infinity, you could think about the graph and be like, oh, hey, that's equal to positive infinity. You could also think about the limit written in this other form. Where then you're like, if I think about taking the limit of the numerator and the limit of the denominator, and you maybe aren't necessarily writing this step out, but you're like thinking about it. Well, then you're like, okay, this goes to 1. This would go to, like, either from a numerical perspective of, like, if I were to plug in negative 1 million, wouldn't that be 1 over e to the 1 millionth power? Or negative 1 billion? That would be 1 over e to the 1 billionth power, where those values for e to the x would just be getting smaller and smaller and smaller, approaching 0. So this you could almost think of it as like 1 over 0, and we've dealt with when we have a non-zero constant over 0 before, like from a direct substitution perspective, which like using direct substitution for infinity is kind of weird to think about, but that's kind of what we're doing. When we've done this previously, don't we know when we get a non-zero constant in the numerator and then 0 in the denominator, we're like, hey, this limit is either positive or negative infinity, right? This indicates that the limit is positive or negative infinity, and if you wanted to use the approach that we previously did of test values, like if we were to use plugging in like negative 1 million, right? We're like, okay, 1 over e to the negative 1 millionth power, and we're just checking signs. This numerator would be positive. The denominator would also be positive, indicating positive over positive. This would be positive infinity. Did we follow that? So this isn't for vertical. We previously looked at when we ran into this with direct substitution. When you got a non-zero constant over 0, you're like, oh, there's a vertical asymptote there. But because this is, as x is approaching infinity or negative infinity, it's not a vertical asymptote. Like, we're still thinking end behavior, but we can kind of in the same thought process be like, hey, what happens if we were to think about, like, in quotes, direct substitution of infinity or negative infinity, and you run into that non-zero constant over 0, the limit's still going to be positive infinity or negative infinity, and you just have to think about which sign you would end up with if you're plugging in like those really small values or those really large values. Questions? Okie dokie. Are we awake?
No. Yes.
Sort of, kind of. Sine. Think about sine as x approaches infinity. What's happening to sine as x approaches infinity?
It's looping.
It's looping? I don't know if it's oscillating. I would say it's oscillating. Looping, I think about it like almost like going around and around and around. But I guess if you're thinking about unit circle values, okay. So if sine is oscillating, and it's oscillating between -1 and 1, right? Is there ever a way that you could determine one specific value that sine is approaching? No. Meaning all we can say, and get rid of your equals, nope, is DNE, and that's because oscillating between -1 and 1. Sine is oscillating between -1 and 1. So the limit is d and e, which tells us something about the end behavior, right? Like the fact that the limit as x approaches infinity is d and e and not infinity or negative infinity, like that tells us something. Are you just going ahead so then you can be like,
No,
hey, was I right?
Question marks because I'm.
I know, but you're like trying to think about it before we get to it.
Yeah.
I respect that.
That's-
Okay, next one is also really interesting. So you look at this and you're like, okay, as x approaches negative infinity, sine would be oscillating between -1 and 1, right? But then as x is approaching negative infinity, those values between -1 and 1 are being multiplied by the x value. So like being multiplied by those really small values. So like what would be happening to the graph? It would be oscillating as x approaches negative infinity between positive and negative infinity. And this makes sense, right? Isn't that cool? Like if you look like close up, like close to the origin, not that interesting. You're like, okay, yeah, I see there's some oscillation that makes sense for sine. And then you're like, whoa.
Whoa.
And that makes sense, right? Like there would be a point of intersection with all the high and the low points with either y equals to x and y equals to negative x. So as x approaches negative infinity, this limit would still be d and e, but for a slightly different reason, and that reason matters leading into our next limit. So d and e, because oscillates between negative infinity and positive infinity. Okay, are we listening? I know you've already thought about it. Some of you have already thought about it. But this next one, you're like, hey, sine of x over x, I'm familiar with that. But this isn't the special trig limit. Why is it not the special trig limit?
Because it's not.
What's not 0?
X is not 0.
Yeah, x isn't approaching 0. X is approaching infinity. Okay, so yes, as x approaches 0, sine of x over x, we know is equal to 1. We've seen the graph, we memorized it. Later on, we'll be able to prove that analytically. So we're thinking about end behavior, sine of x over x. So one way that you could think about this is like separating this into a product of two limits, like the limit as x approaches infinity of 1 over x times the limit as x approaches infinity of sine of x. And you're like, well, we just talked about this one, right? It was d and e because oscillates between -1 and 1, right? But as x approaches infinity, sine, those values are oscillating between -1 and 1, which are all constants. Whereas as x approaches infinity, what's happening to 1 over x? It approaches 0. So if we think about these values that are switching back and forth between -1 and 1, but then is being multiplied by really small, like by 0, values approaching 0, this limit just ends up being 0. That's kind of a, almost a numerical approach. If we wanted to evaluate in a more analytical way, you could use something you're familiar with. You could start with the fact that sine is between -1 and 1, which means that sine of x over x would be between -1 over x and 1 over x. Do we see where I'm going with this?
Yes.
The limit as x approaches infinity of negative 1 over x would be 0. And the limit as x approaches infinity of 1 over x would be 0. Which means we can conclude by the squeeze theorem that the limit as x approaches infinity of sine of x over x would also have to be equal to 0. Squeeze theorem can be used to prove the existence of a limit. It can't be used to prove the non-existence of a limit, though. Now, the difference here, like this would be fine. Like thinking about it this way, this wouldn't have been the same if this were a limit where it was d because it's oscillating between negative infinity and infinity, though. Like, this ended up being equal to 0 because this function was oscillating between negative 1 and 1, right? Like oscillating between two constants. Are we doing okay? Am I going too fast? It's like kind of familiar, right? We're like, hey, limits and behavior, putting it all together. Okay. We last year had kind of referenced this definition, but we didn't have limit notation. So what this says, this statement says, is basically if this is true, then this is true, and it goes the other direction too. If this is true, then this is true. So if as x approaches either positive infinity or negative infinity, you get a limit, like the limit exists, then you can say that the function has a horizontal asymptote at y equals to L. A function can have at most how many horizontal asymptotes?
1, 3.
1.5.
Oh, 2. No. Infinity.
And what, like end behavior, yeah, so like what if as x approaches infinity, a function approaches 2, and as x approaches negative infinity, the function approaches negative 2. In that case, you would end up having two different horizontal asymptotes, right? There's two directions. If a function's domain goes from negative infinity to positive infinity, there's two potential directions that you're considering end behavior for, where there could be horizontal asymptotes, right? So since we're thinking limit as x approaches infinity and negative infinity, there could be one, like when we've studied rational functions, there's only been one. Like a rational function will only have one horizontal asymptote, which is a ratio of two polynomial functions. But if it gets a little bit more interesting, and we'll look at some of those next class, there could potentially be two horizontal asymptotes. Squeeze theorem. My little blurb at the bottom is just, it's kind of what I get frustrated about with these different algebra and pre-calc textbooks that introduce horizontal asymptotes and vertical asymptotes at the same time, which I understand because they're both like these imaginary lines that guide the behavior of the graph. But remember, a vertical asymptote is a type of discontinuity. A horizontal asymptote I refer to as an end behavior asymptote, right? It describes end behavior. So a function can cross a horizontal asymptote because it doesn't mean anything in terms of discontinuity. All it means is that the function is kind of looking like a horizontal line if you were to zoom out on the graph. Like if we looked at the graph of sine of x over x, Jack. Okay, so if we look at the graph, so up close, this is the part that we looked at when we were talking about that special trig limit, right, as x approaches 0. But like if we were to zoom out, doesn't it almost look like you're just looking at a horizontal line at y equals to 0? And that's the idea behind these end behavior equations, is if you zoom out, the function starts to look like that end behavior equation. That's why we're able to use the end behavior equations, which are sometimes lines, which we refer to as asymptotes, as being a description of the end behavior of a function. Questions? So let's look at some rational functions that you've previously studied. And let's talk end behavior. So again, now anytime you're thinking end behavior, I want you to think if it's a function whose domain goes to negative infinity or positive infinity. It doesn't matter if there's domain restrictions kind of locally around the origin, but like if we're thinking of a function that does go to negative infinity and positive infinity, then we're thinking for end behavior, limit as x approaches negative infinity and limit as x approaches positive infinity. And again, definition of a rational function is a ratio of two polynomial functions. And thinking about limit properties, right? Like if we were to think about taking the limit of the numerator and limit of the denominator, and we think about the polynomial that's in the numerator, the terms being at a tug of war with each other as x gets infinitely large or infinitely small. In the numerator, which term's going to dominate the other terms? The 3x squared. And then the denominator, 5x cubed would. So the end behavior model.
Isn't there like another way to do this using like algebra 2 or something?
What, like memorizing the relationship between the degrees, which just kind of goes back to end behavior model. So if we have y equals to 3x squared over 5x cubed, what's that simplify to, you guys?
3 over 1.
Okay, which is just the graph of 1 over x transformed, right? So this is a simpler equation that we can reference for end behavior that has the same end behavior as the function that we're trying to determine end behavior for. So like this, 3 over 5x, right? If you're thinking about 1 over x being what, vertically stretched by a factor of 3 and horizontally compressed by a factor of 5, like there's no shifts or anything. That means that as x approaches positive infinity or negative infinity, this is approaching 0. So that means that these limits would both be equal to 0. Now I'm not sure, I know Mr. Green did these limits differently. He used to, when he taught AB, I know, think about like dividing each term, like how our textbook does. If you look in the textbook and you think that method makes more sense to you for evaluating these limits, that's totally fine. Like you would end up dividing, I think, by x cubed for each term and then taking the limit. Or maybe he had just like thinking about the degrees of the numerator, degree of the denominator. I think that's how, when I've observed in the past, I think that's how he did it, which is how the textbook does it. If that makes more sense to you, like totally fine. I think that end behavior model kind of jives with how I've taught it, like how we've talked about end behavior previously. So that's how I like to think about it.
Isn't there like certain rules, like numerator degrees like bigger than
Right, but doesn't that just go back to like thinking about like what the end behavior model would be? Sure, if you want to think about it that way, go for it. It gets tricky when we start looking at the more complex fraction. Hey, when we start thinking about the more complex looking functions that are fractions but not necessarily rational functions, I think end behavior model is really useful. And I don't think that method, I think that method is fine for rational functions, or way of thinking is fine for rational functions. But if you get into kind of more complex rules of functions that have fractions, I think the end behavior model kind of makes more sense. So kind of putting this together, hey, both these limits ended up being equal to 0. So what can we say, what equation describes the end behavior of f of x? There's a horizontal asymptote. Going back to that definition, that means there's a horizontal asymptote. Can't write. Sure. At y equals to 0. And that's kind of understood amongst us. When I say there's a horizontal asymptote at y equals to 0, it's understood amongst us that, hey, that describes what the end behavior of this particular function is. Like that gives us a picture and a way of describing the function's end behavior. Okay, and again, my end behavior model came from taking that ratio. In the function g of x, we're also thinking limit as x approaches negative infinity and positive infinity. Our end behavior model here, looking at in the numerator, the term that would dominate as x gets infinitely large or small would be 3x to the 5th, and in the denominator would be 5x to the 5th. So the EBM, which is side work, it is not graded work, would be 3x to the 5th over 5x to the 5th. What does that simplify to, you guys? 3/5. What's the graph of y equals to 3/5 look like? What type of line?
Horizontal.
A horizontal line. So g of x has the same end behavior as the horizontal line y equals to 3/5, which means g of x approaches 3/5 as x gets infinitely large or infinitely small, and also indicates that there's a horizontal asymptote at y equals to 3/5. Next one we're going to end on for today, but h of x. So again, thinking limit as x approaches negative infinity of h of x, as well as the limit as x approaches positive infinity of h of x. Thinking end behavior model, which is side work, I'm like, okay, this ratio here. So y equals to 4x cubed over negative 2x squared, which simplifies to be what? Negative 2x, which is a line with a negative slope. So this rational function has similar end behavior to the line y equals to negative 2x, so a line with a negative slope, meaning as x approaches negative infinity, h of x would approach infinity, and as x approaches infinity, h of x would approach, okay? There would be no horizontal asymptote because those limits, neither of those limits exist. Kind of going into, we'll talk about this next class, like what equation can we use to describe the end behavior of this function? Exactly. So the end behavior is going to look linear. The slant asymptote is not y equals to negative 2x, but this is where we'll leave off and we'll get into next time.